events, and instead ran all of its events in France. The Monaco Club immediately sought to rectify this, not letting the country's area of barely 1 square mile get in the way. They picked the 2 widest roads in the city as the basis for a racetrack and started holding the Monaco Grand Prix. The problem is that those 2 streets were directly next to the harbour. But the first event in 1929 was successful, and so they kept running it and rerunning it. This photo is from the 1931 event, and you could see the logistical problems here. There are trees on our left, and there's the harbour on the right. It's not a terribly sensible location, but they needed to run this race here so that they could have control over the rally, which was the race they actually cared about. You can see up the back here, that's a hill with a corner and a significant couple of direction changes leading onto the harbourside straight. There's a braking zone and a turn that would leave you pointed at the harbour until you recovered and pointed back towards the racetrack. Now back to the track. Now see on the right there, the track limits, the only thing keeping you out of the water were some sandbags and ship moorings. An incident was only a matter of time. In 1955, Alberto Ascari misjudged his travel down the hill and only managed the first of the 2 direction changes and flew straight into the harbour. Thankfully, Ascari was thrown from his car, seatbelts not being a thing at the time, and swam to shore. Australian driver Paul Hawkins managed the same in 1965, somehow going over the top of the edge of the circuit, now marked off with hay bales instead of sandbags, much safer. But clearly something needed to change. Hay bales weren't enough, and solutions like portable concrete barriers, though good for stopping cars from going over the edge, had undesirable side effects. The solution came in the form of the steel traffic guardrail, marketed at the time by the Armco Steel Company of Southern Ohio. The W-shaped cross-section absorbs head-on impact slowly, and by bolting spans together, impacts can be absorbed over a significant distance, reducing the travel of the barrier at the point of impact, making it far more likely that the car and the driver would remain within the bounds of the circuit. By 1971, much of the circuit was surrounded by Armco barriers, and while that section at the bottom of the hill remains a hotspot of incidents, there hasn't been an incursion into the water since 1966. But beyond safety, the presence of Armco barriers had some significant side effects. By being as tall as the cars, they gave visual indicators of where the track limits were, allowing drivers to brake more precisely. Racers and the cars adapted, and within the decade, speeds at Monaco exceeded the pre-Armco days. Barriers also greatly reduced the scope of incidents on the racetrack. Cars would now remain within the confines of the track, and this predictability means that today, marshals at that circuit are able to clean up after most accidents in a handful of minutes. And thanks to their deployment at racetracks, today Armco barriers are used throughout the world as a way to reliably stop people from driving off the road in otherwise dangerous places. So that's enough about race cars and the problems that they have with the sea. And now let's talk about programming and the problems that we have with the sea. C, more than any other programming language before or since, has shaped how we think about writing software, and that's not without its consequences. C was deliberately a very small language, and most features in the language roughly correspond to the features of one specific CPU. The remaining features were built around code organization so that you could keep your programs in your head. And this stood in stark contrast to other languages at the time that were not focused on the computer's capabilities, but rather the domain. So think COBOL for business applications or Fortran for scientific processing. So access to the full capability of your computer was great. But being able to do anything that your CPU can do means being able to do anything that your CPU is willing to do, including things that are undesirable. It's easy to make something that doesn't work entirely as intended. This is some quite reasonable C code that can easily access memory that it's not allowed to, and your program will die if it does. You actually have to think about what your program is doing in order to avoid an error that stops execution. So all too often, the intent of code gets obscured by defensive error handling. Or to put it another way, the act of understanding the effects of a program or how to use a language or a library effectively is not the same as the act of writing code itself. It's not trivial to use a function in a C library without reading the documentation for that specific function. This might sound flippant, like we should definitely read documentation, but documentation in that case has to convey all sorts of minutiae that get in the way of thinking about what your program does. The consequences of not deeply understanding the contract of a C function are worn by you, and they can frequently be unpredictable. And the first generation or two of languages after C sought to solve incremental problems: better code organization, better portability, better text processing, no need to compile, better data structures. But each of these languages, and certainly in their early days, were still geared towards the same philosophy of program. Your code has a universe of effects, and it's up to you to make sure that your program doesn't touch dangerous or broken situations. So take this two-lined piece of code in Python, for instance. I count at least 2 potential error scenarios in this code. What if example.com times out? What if the URL doesn't return a valid JSON object? This code runs just fine on the happy path, but it's up to you to infer where errors might occur and program defensively. Okay, and you can fix this with a blunt instrument, but this is really no better than the first case, other than that you get to write your own error message. So what? You can start scoping your exception blocks tightly to each error point, and that itself gets to be tedious. So in Python, your options are either to be permissive and let your routine die weirdly, or be exceptionally defensive and handle every possible error scenario. If you care about your programs not throwing exceptions, you should be doing the latter, but the tools that we've grown to use require us to predict where exceptions will occur and fortify that code. And that's what it means to work safely in Python. You're producing code that doesn't blow up, end unexpectedly, or have unpredictable behavior. And it's where we as programmers have to do the work to ensure that our programs behave correctly. And then we have to do work to communicate how to use our programs correctly. Or put another way, we have to document what our program does and how to make it do what it should do, and we need to test things to make sure that they do the right thing. And neither of these things are bad in and of themselves, but without appropriate tools, they are incomplete and insufficient. So the general approach to testing is that you write a bunch of cases, and each case represents a fraction of the code paths that your program could take. And we definitely have tools that can tell us about how much of our code base was exercised under test conditions. That's what code coverage is. But this approach to testing is invariably reactive. Even if you follow test-driven development, if you notice an error condition after the fact, you still need to patch it with other tests because you haven't considered the full scope of bad behavior. And code coverage is only a useful metric across your own code base. It does not tell you anything useful about how your dependencies will interact with your code. Making a test suite that covers 100% of your dependencies code paths that your code can exercise is basically futile. Do you know every place, every library you use will throw an exception? This is not something that Python is any good at communicating, and it makes guaranteeing that our code is safe a process of guessing. And because most Python code does not communicate its structure completely, this means that instead of documentation that can focus on use cases and intent, you must explain the shape of your library or program before you can explain how it works. But this documentation is decoupled because the act of explaining how to program is separate from the act of programming itself. If a program evolves but the documentation does not, then users can't figure out the structure of that program, let alone how to interact with it properly. And most failure cases for documentation are these structural failures rather than misdocumentation within a correct structure. So this is ineffective. The normal way of programming is that structure is communicated implicitly, and the only foolproof way of determining that structure is by interacting with it. Because when structure is not revealed directly, discovery inherently becomes a process of trial and error. So communicating structure and interacting with that structure should not be separate acts. What we need are tools that communicate structure for us, make it clear where the safe places to work are, and leave errors predictable. What we need are guardrails. So what do guardrails for computer programs look like? Well, guardrails for programmers are the same as the guardrails I talked about earlier. They use structure to show you what is guaranteed to be safe. They limit the range of undesirable consequences, and in doing so, they make it easier to reason about possibilities. In short, guardrails are features that use structure to show you what is possible and what isn't, and in doing so, guardrails guide you towards more correct programs, often by letting our computers figure out automatically whether we're entering unsafe territory and ruling those spots out. So over the last 2 decades or so, rather than adding features to let you take advantage of new things that Python couldn't let you do before, Python has steadily introduced guardrails as first-class features in the language. These are tools that help us interact with Python better and communicate our intent to others better and avoid undesirable side effects. So let's look at 3 features of Python that you may already be familiar with and explain how these serve as guardrails. So the with statement is the first guardrail I want to explore, and to explore that we need to look at the risky behavior it replaced. So with statements are used to handle resources that need to be acquired or released, things like locks, file handles, sockets. It's actually really hard to get the life cycle of these sorts of objects correct. Say you open up a file handle, you write to that handle, and then you close the handle. So if everything goes well, everything is fine here. But what if it doesn't go okay and you can't write to the file? Well, you get an I/O error. So how do you handle this particular I/O error? This is where things start to get difficult. Do you put the handling outside the try except block? This is all very good unless you want to propagate that error up through the stack. So you might put another handle.close inside the except block. This is slightly more correct, but as you can see, it's starting to demand a lot of the developer to get this exactly right. And so that's why we have try except finally. Whatever's in that finally clause will get run when you leave the block. And this is great for making sure that resources get cleaned up properly when you're done with them. But there are several problems with this. The first one, the biggest one, is that you need to know about try finally before you can actually use it. It's difficult to read. Like, does the except block get handled before or after the finally block? I couldn't tell you that. And the other thing is that you can code with try and except, or even without try at all, and you'll have something that looks correct on the happy path, but has subtle bugs. So this is a trivial feature where incorrect usage is more accessible than correct usage. And so this is likely to be a source of bugs. So we got the with statement instead. The handle for a resource is valid when you enter the with block and it becomes invalid as you leave the block. You get a visual reference to where it is safe to work with the handle and where it isn't. The with statement is a guardrail. It uses structure to show you the life cycle of a resource. It builds correct error handling into the structure of your code so that even if you don't do any error handling yourself, the resource gets managed correctly. And it makes it even easier to reason about where to put your exception handling. If you need access to the file handle in your error handling, you put the try except inside the with block, and if you don't need the handle, you put it outside the with block. It actually becomes easier to reason about execution order as well. And because Python is showing you how to use its feature, it's actually much easier to write code that gets it right the first time than it is stumbling into correct behavior through trial and error. So the with statement is a guardrail. And it's a guardrail that you can build into your own code quite easily. You can look up the documentation for contextlib.contextmanager if you want to incorporate this into your own code. Async functions are an interesting feature because they're an example of a way to introduce guardrails for a piece of machinery that already exists in the language. So async functions can only be called in an async context, an event loop, something like that. And the async await syntax gives you the tools to make sure that you're using async and await in the correct way. You can only await a call if you're in an async function. This both makes it clear that you need to use async functions together with other async functions, but also it gives you some structural indication of where you are yielding control back to the event loop. And this compares really favorably to the previous way that async coroutines worked in Python, which was to make use of the generator syntax and this yield from construct. It's not immediately obvious to someone without access to the source code that this function here is asynchronous, okay? But it is. You can trust me on that. And so to effectively describe something as asynchronous, previously you had to either provide docs that pointed out that something was a coroutine, or you could use names, or ideally you could do both. And there's no language level barriers that prevent you from accidentally awaiting something that isn't itself awaitable in the same way. So async await gives you both a convenient programming construct that lets you communicate that you're doing things asynchronously, but it's also one that lets Python verify that what you're doing actually makes sense. Now, guardrails don't just show you spaces that are explicitly safe. They also make it clear where things are not safe. Decorators show you that a piece of syntax that's normally straightforward to understand is about to be subverted, and that you need to make extra effort to understand what's going on. They highlight places of risk rather than expose places where there is a lack of risk. So decorators exist because Python lacked features like class methods or static methods that other languages have. But it was possible to implement these at runtime. But to do that, what you would need to do is define a method inside a class, and then after defining the method, assign the decorated method back to its original name. And there's a lot to hate about this particular pattern. You're changing the semantics of a feature of the language at runtime, but this feature is genuinely useful. What's particularly bad here is that the confusing thing happens out of sight of where you're defining something that looks like it should behave normally. And if your method is really, really, really long, it can be difficult to someone reading code to notice that this decoration is even occurring. So having the decorate syntax available in Python makes it so that you can put the thing that's potentially confusing up front and make it more obvious to people reading your code what is going on. But in and of themselves, decorators still don't tell you what's being changed, just that something is going to be changed. So if you're writing your own decorators, it's still not immediately obvious whether your decorator is going to return a similar function or whether you're going to modify things further. And this is where another of Python's guardrails come in. You can use static type hints to communicate structure in a way that will be communicated to people who read your code. If you have a decorated thing that's going to behave broadly similarly to the function that you wrote in the first place, you can use bounded type vars to show that. And it can be really clear if you're going to do something that's completely unexpected, like evaluate the function and store it back to its name. You can show that with a type signature. And so Python has been evolving as a language. It's gone from being something that's C-style and an open field where all possibilities are open to you, and it's up to you to figure out whether something is right or wrong just by playing around with it, to a language with constructs that show you how to safely use them and highlight risks or unexpected behaviors where they occur. But there's still a lot of historical baggage in our language, and you have to coexist with this historical baggage. So you can build your own guardrails into interfaces that you develop, and you can experiment with other people's interfaces using defensive coding techniques based on those guardrails as well. So who's seen this trick example that you get when learning Python? Or something similar to it? Like, what happens when you make a list, assign that list to another variable, and then amend the second list behind that second variable? The answer is that because Python treats variables as references to objects, a list and another list point to the same object. And this is true of built-in data structures, and it's true for your own classes. And because you're an experienced Python developer, you know how to avoid this in your own code. But what happens when you import someone else's function and you pass your list into that function that you got from someone else? At that point, you're trusting that the implementer does what they're saying they will, and that they're not completely incapable, and that nothing unexpected is going to happen here. And much of the time this works out, particularly if you have good tests against that library. But what if you want more guarantees? Consider using immutable data structures where you can. If you've got a list, pass in a tuple instead. If you've got a set, pass in a frozen set. If you've got a dictionary, consider using something else immutable. Key value pairs in a set. or rewrite it as a concrete class using frozen data classes. All of these data structures enforce immutability at runtime. So by passing in those sorts of structures, you'll discover through errors being raised everywhere that they are making changes, and you have to be defensive. Through experimentation, at the very least, you can discover if you need to make a copy of things or plan for contingencies. But what of your own interfaces? Well, static typing is quite a powerful guardrail. You can directly express to your consumers exactly what operations you're willing to perform on an object and let them make their own decisions. If you're dealing with standard data structures in Python, there are abstract types in the typing module that cover mutable and immutable versions of these without depending on a specific structure type. But what if you've got a class of your own? Well, recent versions of Python support structural subtyping in the same way that Go does through a feature called protocols. So if you have a class that has an interface like this, you can write a protocol interface that describes the things that your function is going to work with. And then your type checker can verify that your class matches the protocol. And more importantly, it can do this for classes that you didn't write, written in contexts that weren't aware of your choices of types. And this is great, but this example here doesn't help with immutability, but you can fix that too. You can just use @properties in your protocol, and that makes the type checker verify that you aren't going to write to that attribute. And so with protocols, you can make your contract with your code's consumers explicit. You can show them exactly what parts of the interface you're going to use, what you're going to do with them, and you can automatically verify that your side of the contract is fulfilled, which gives your consumers a clear idea of what they need to test to have good confidence that their code is going to work with your library. And the last idea I want to touch on is the big one, expressing and handling error states, because this is what working safely is about, making code that doesn't fail randomly because you failed to predict that a certain library would throw an exception. Which is difficult because Python's most obvious tools for handling errors is the exception, and it's not really a very good one. They interrupt the flow of code. Handling them efficiently is not particularly easy, and for the purposes of this talk, it's unpredictable when they can occur. They're meant for exceptional situations that need special handling, but Python uses them for most errors. And this unpredictability is not a new thing. Like Java has had its own guardrail for handling exceptions since the early days, this thing called checked exceptions. So if a method says that it can throw an exception, somewhere in the call chain has to catch that exception. And this sounds great until you have to catch 6 or 7 different types of exceptions, and your code tends to end up being more exception handling than actual logic. And if you're dealing with a situation where an error state is actually part of the normal and predictable flow of your code, you have 2 choices. You either have to code defensively by using like if statements and such, or you have to litter your code with exception handling. And this makes us complacent to when errors, like actual errors, are likely to occur. It's much easier to just ignore it, and I've lost track of the number of times I've let code that effectively lets an obvious exception into prod because it was much easier to do that than remember that a particular function might raise a value error or something like that. A trick that's popular in functional languages and more recently in Rust is to use result types as return values from functions that often return errors. The basic idea is that a function can either return a success or a failure value, and your code has to acknowledge that before you can read the success value. In Python, you can do this with union types from the typing module. And if you want to code quickly and you can tolerate your program blowing up, well, you can do that explicitly with an assert, or we can use some conditionals to handle it like a variable. And that's it. Like the type annotation here shows you that there is an error condition that you need to handle, and you know that you have to handle that error. And more importantly, the type checker also understands that there's an error condition to handle, and your code won't pass type checking until you write code that acknowledges that possibility. And this gives you so many more guarantees than you'd get if you solely use exceptions. This approach also lets you reserve exceptions for cases where it truly doesn't make sense to carry on. So both immutability and result types do a couple of things to how you work safely with each other's code. The first is that by conveying structure in code that you can read and a computer can verify, there's less need for documentation to explain edge cases. If a function won't mutate an argument, you don't need to explain that. If a function can return an error as a return value, that can be automatically verified, and you don't need to explain that an exception can possibly occur. And being able to verify that you're handling all possible output cases from a library means that you can actually trust that code coverage is giving you a useful metric when you're interacting with that library. So that's an example of a selection of 5 examples of guardrails. These are all examples of using programming constructs to convey the structure of functions to the people who call them, so that you can understand what to test and focus on using documentation to give tactical understanding rather than merely an understanding of structure. And these examples show that Python cares about using structure to communicate how your code works. New language features are, more often than not, features that give humans better ways to manage the structure of their code, rather than simply expanding to allow all the features that our computer might have. And sometimes there are duplicated features. The first way to do something might be a way to enable some behavior at all, like think try finally or think yield from. But they're really features that are there should you happen upon them. Context managers or async await actually show you how to use them. And so it's clear from reading code that you're using things correctly. And that's how you should be thinking about selecting which Python features you use. Python gives us guardrails and gives us tools to make our own so that we can spend less time understanding the space we work in and actually instead go and do that work. And just as Python gives us the tools to work more safely, we ourselves can structure code so that other people who interact with our code can understand the assumptions that are baked into our code just by looking at the structure that we expose, allowing them to write safer code with more focused tests. And so yes, testing is still important, but having verifiable structure tell you what is possible and what isn't means that you don't have to write all the tests. Like, if there's no chance of an exception popping up, you don't need to test that an exception is going to pop up. And so documentation can, rather than describing the structure of a function, focus on the why and the how of a function. Documentation still needs to exist, but the focus no longer needs to be on things a computer can understand for you. It can be tactical or communicate intent instead. And so signs are, like, in most cases, we've outgrown languages that merely expose the capabilities of our computers and trust us to understand the structure that we need to put in place to harness those capabilities. Instead, languages that give us constructs that let us use computers safely are taking hold. Now, Python, being a language that emerged in the shadow of C, but has stayed relevant for more than 30 years, gives us both options. So you can do whatever you want and wear the risk of unpredictable errors, or you can use the guardrails.
Thank you. We have time for one quick question.
Ooh.
So when you started talking about guardrails, the things that popped into my mind immediately are examples where Python explicitly chose not to impose guardrails. Think about privacy on data class, on class membership, for instance. Privacy, there's no private declaration on members of a class, for instance. And types in general are like a late addition to Python and still partially adopted with no adoption no effect at runtime. You know, protocols are a suggestion to MyPy. It doesn't prevent my code from running if I don't use MyPy running incorrectly. Do you think that the Python community's attitude towards guardrails, it obviously has evolved some. Does it need to evolve more? Are you...
Well, so there's a reason why I chose this analogy, which is that, like, if you're in a car, you can still drive through a crash barrier. It's that all these features are things that provide you with direction but doesn't stop you from doing bad things. And I think that's been a thing that Python has sort of had as a philosophy that's been a through line for its entire existence. It's just there are now more features that show you structure that you can use, so you can use it correctly should you follow that structure. And, like, I don't think that's something that's going to change, but generally speaking, if you do the right thing, the thing will behave correctly.